Welcome back, everybody, and welcome to the last two sessions. The topic today, as you can see from the Jupyter notebook here, is to give first a short repetition from last week about what we did with copper cluster theory, in particular the connection to the pairing model. And then we are going to look at copper cluster theory, singles and doubles excitations, and we're going to view that one first from a diagrammatic expansion point of view. So how to use diagram rules to actually set up the final equations, which we are going to encode. And then while we do this, we're also going to go through the nitty calculations of the equations using a standard algebraic approach. And when we increase the complexity of the model by adding more and more correlations through the T operators, then we're going to get more and more complicated equations. And at a certain point, we actually have to stop. So I wanted to give you a kind of a quick reminder from what we did last week. So I'm going to jump back to the slides for the Jupyter notebook from last week. And one of the things which we did then after all these basic reminders on matrix elements and what is a good and bad Hartree-Fock basis, etc., etc. And we then went into a discussion of the exponential ansatz. So I'm going to scroll through a little bit here. And the thing which we did then was to make a pretty rigorous statement about the exponential ansatz as another way to represent the exact wave function. And in this particular case, we are looking at the exponential ansatz. We did a comparison last time with the standard expansion we have with an FCI calculation, which is a linear expansion in the unknown coefficients, which we get from diagonalization. And then we showed that we could relate the amplitudes, as we call them, in the operator T, which then represents different types of excitation level. So T1 is then a one particle, one hole excitation. T2 is a two particle, two hole excitation. And if we have n particles, we can make n particle, n hole excitations around the Fermi level. So this is in particular dedicated, the discussions here are dedicated to fermionic systems. Now, one of the things which we did last time was also to derive the equations which we end up having to encode. And the way this was done was by what we call a projection technique. This led to the definition of a Hamiltonian, which is given by the normal order term, which then excludes the reference energy, which is typically included in the calculation of the total energy. So we have an expression for delta E. When we did that, we defined this Hamiltonian in terms of this coupled cluster amplitude or exponential ansatz. And then we could define a transformed Hamiltonian through this specific similarity transformation. Now, in order for this transformation to preserve hermiticity, we then have some simple mathematical requirements on this operator T that it has to be anti-Hermitian. Now, in copper cluster calculations, since this T operator here does not in general commute with the Hamiltonian, it means that when we write this exponential expansion, we will not have an expansion which truncates at a given level of nested commutators. So we invoked what is called the Baker-Campbell-Hausdorff expansion, which I will remind you a little bit about a little bit later here. When we did that, we get an expansion in terms of commutators of the operator T and the normal ordered Hamiltonian, which does not necessarily commute, in particular terminate at a given level of nested commutators. In particular, if we choose this h of n to be Hermitian, that series of nested commutators does not commute. However, if we choose to not respect the hermiticity, then we can show that that series commutes at a given order. This, however, comes with a price, and the price is that the theory is no longer variational, as we also experienced when we did many-body perturbation theory. So many-body perturbation theory, as you also saw from the second midterm, does not obey the variational principle. And some of you could see that sometimes it could converge from below and sometimes it could converge from above. So these are some of the problems which we have to live with in a way, with machineries which are flexible to implement and easy to implement. Coupled cluster theory gives us a systematic way to include more correlations, but there's a price which we have to pay, which is the anti-hermeticity, no, the non-hermeticity. This can, however, be mended, and there are actually many approaches which deal with the improvements of the theory. If you're dealing with, instead of many-body perturbation theory, if you do Green's function theory, then hermeticity is normally respected. However, even if it's non-Hermitian, the eigenvalues are conserved with this transformation, as we also saw last time. So what we ended up with then was to define this cluster operator in terms of one particle, one hole, two particle, two hole, etc. So with the exponential ansatz, what we end up with then, as we showed last time, we end up with the possibility to, due to the exponential character of the ansatz, we can then produce this type of excitations to infinite order. So remember now, if you look back to the second midterm, when you looked at the many-body perturbation theory, we computed two particle, two hole excitations to second order. We did that to third order and to fourth order. And all these gave us improvements to the final coefficients. However, there was no guarantee that it would converge. What we often see in physics is that excitations of the two particle, two hole type, they play a very important role in the calculation of the correlation energy. So coupled cluster theory through the exponential ansatz means that we're actually summing to infinite order a given set of correlations. So the type of amplitudes, as we call them, if we now think back to the different states which we have here, these amplitudes TIA, which represents a one particle, one hole amplitude, and the two particle, two hole one here, these are unknown quantities. When we diagonalize in FCI theory, what we have then is that we get these coefficients directly as the coefficients of the eigenvectors. Now, what we did then was to calculate with this similarity transformed Hamiltonian. We showed last week that we actually could then set up these equations here. And these are the equations, if you now think of your Hamiltonian matrix, we're actually not taking the Hermitian conjugate of this expression, which means that if you set up your Hamiltonian matrix, it's only the row part here which is taken into account. And this is the one which is driven to zero. We don't know whether the conjugate of this one is zero or not. Actually, the solutions may of the left eigenvalue and the right eigenvalue problems may not give the same eigenvectors. So we set up the correlation energy, and we used, in the derivation of the equations last time, we used what's called the Baker-Campbell-Hausdorff expansion. And the benefit when T is not a Hermitian operator is actually that this series truncates at a given order. So this is one of the key elements of coupled cluster theory in its traditional form, is that the cluster operator consists of sums of terms that consist of particle creation and hole annihilation operators, but no particle annihilation or hole creation operators. That means that all terms that enter T, they actually commute with each other, as we discussed last time. And that means that the commutators in this expansion can only be non-zero because T must connect to H of n, but no T with another T because they commute with each other. And that means that this expansion terminates at a given order of nested commutators. And if the Hamiltonian contains up to a two-body interaction, which means that we have two creation and two annihilation operators, then this series here terminates at the level of four nested commutators. So this is a very beneficial property because we can then use this similarity transformation and set up equations for finding the coefficients. And these coefficients are then found by solving these equations here. And if we stay at the level with one particle, one hole excitations and two particle, two hole excitations, then these are the equations, these three equations are the equation which we end up solving. So this is in a way to just give you the kind of overarching view of what is going on. Now, what we did then was actually to derive last time the so-called equations, which are called CCD, which means that we only include two particle, two hole excitations. So we leave out the one particle, one hole excitations. The equations we end up with then with the unknown amplitudes, and these amplitudes which you see here. So let me just bring back the definitions. If you now look at this slide here, when we now take the T2, we have this operator which you see here. But then the matrix elements are typically defined, this FQP, this is just a shorthand which we are using. They are given in terms of H0, or if we don't have an external potential which confines the motion of the particles, is then given by just kinetic energy. But in our case, we have often thought of a system where the particles are trapped by some kind of external potential. It could be a harmonic oscillator potential, or it could be the field which is set up by the atomic nucleus in atomic physics and molecular physics. And the reference energy is defined as you see here. So that means that if we go back to the Jupyter notebook, we have this one-bodied part of the Hamiltonian which kicks in. But if we now want to look at the case which we had in the midterm with a pairing model, then all these terms here, they are actually zero. So they disappear in the calculations. So we can leave out many of these terms. And there are also matrix elements here which will give non-zero contributions. And in particular, there will be matrix elements which where we connect particle states with Hall states. So this specific matrix element can be non-zero because we have two particle states going to two particle states, if you think of the pairing model. The same applies to this one because we have two Hall states going to two Hall states. On the other hand, this contribution here for the pairing model disappears because you see we have a particle Hall state. And when we then specialize to the pairing model, there are specific terms which disappear. Now, these functions PAB means that we interchange particles A and B. So if we use this is a permutation. So that means that this is actually 1 minus the case where we have interchanged A and B. So if you look at this equation here, if we interchange A and B as external lines, that will give rise to a minus sign due to the fermion antisymmetry. And the same with IJ here. So last week we did actually write out in full detail these equations. So let me bring back some of the equations which we ended up with last time. And this is taken from the handwritten notes. So if we go back to the handwritten notes here, let me just scroll down a little bit. We went through the different calculations of the CCD approximation and calculated all the different transition probabilities for these specific matrix elements. And when we collected everything, we had one term here, which contains just a single particle energies. We have the unknown amplitude, and then we have this specific matrix element here. And you can see the matrix element, if you go back to the equations here, this is the specific matrix element. So this is actually the Hamiltonian we're setting up. And then we had a contribution here. And then we had the next contribution, which are the same as you have here, this term and that term. So these terms here, they disappear due to the property of the Hamiltonian which we have. And we end up with contributions like this one, which for the pairing case, the first one here, is 0. So all these terms which you see here, this 1, 2, 3, and 4, with particle Hall matrix elements, they are then linked and brought together in terms of these operators PAB and PIJ. So you can actually collect all these terms in terms of those specific operators, because you have 1 minus the interchange of A and B and times 1 minus the interchange of I and J. That gives you 4 terms. And these are the 4 terms which you see 1 here, 1 here, 1 here, and 1 here. Now for the pairing type of Hamiltonian, these terms all vanish because they mean that we have to break a pair. Then what we will be left with are terms of this type, which you see here with the, so this KL is now a 2-hole state and CD is a 2-particle state. So this is a matrix elements which can be non-zero for the pairing case. And all these coefficients, they represent obviously 2-particle 2-hole excitations, which are multiplied with Hamiltonian matrix elements, which do not need to be 0. Now, when you see this equation, so this is the equation we need to set up to define these amplitudes. And the typical starting point is to ignore when we solve this iteratively, because at the end, what we want to do when we are setting up the problem is to drive this part which you see here to 0. And in this specific case, for the pairing Hamiltonian, we are neglecting, or rather, we don't need to take into account the 1-particle 1-hole excitation, which means in turn that this equation here is not of interest for the pairing Hamiltonian. And then we need only this one. And in order to solve that one, if we now go back to the notes from last week, the typical way you solve this equation here, this lengthy beast, is that you solve this in an iterative way. And you start with a guess for the TIJABs. And a typical guess is, if you neglect all the other terms, is to set that TIJAB is equal to this specific matrix element divided by the single particle energies. And then this term here is nothing but what we got in the second midterm for the term, the contribution to the wave operator from many-body perturbation theory to first order. So that means that a very common approach in coupled cluster theory, when you start solving these equations iteratively, is to use many-body perturbation theory as an ansatz for the first iteration. So then you would simply skip all the remaining equations here, and then simply set TIJAB equal to what you would get from the first order of the wave operator, which you also did in the second midterm. So I'm trying to link everything we do here to the second midterm, because the program which we have in the lecture notes from last week actually do include the pairing model and shows you how you can solve the pairing problem using coupled cluster theory. So the equation then which we need to solve will be, in this case, the equation for the energy. And we would typically continue this iteration till the energy difference, the correlation energy, this EC, doesn't change by a given amount which we have defined. So if we then scroll down here, these are actually the equations which we implement when we are going to solve the pairing problem. And so what we need to do is to have a function that computes the potential. It returns this 4-indexed array, these elements here. So we need all these different elements. We don't need elements of this type or elements of that type, because they are not included in the amplitudes. And then we write a function that computes the Fock matrix. In our case, for the pairing model, we don't even need that one. And then we initialize the cluster amplitudes according to our given guess. And then we solve the equations for the amplitudes iteratively. And what I did here was simply to bring back what we had in the second midterm, and you have all seen this before. So we know the exact solutions here. We know the by diagonalizing. So if we just rerun it, and if we look at the last point, we have a minus 0.3644, which then corresponds to the case where we have 1 here. So in the code below, I've actually included the coupled cluster case with G equal to 1. And then I simply compare that, what I get, by using coupled cluster with doubles only. And as you can see, this pairing model is actually implemented in these lecture notes in physics, chapter 8. And you can actually download it for free. This volume here contains actually a comparison with several many-body methods where we've actually used the coupled cluster method. We've used many-body perturbation theory. We have diagonalization, as you did in the second midterm. But we also included other many-body methods like Green's function theory, and also what is called in-medium similarity renormalization group theory. If you then, in addition to this, want to add more entropy to your system, there is a possibility to solve the same problem using neural networks. And this is a paper which we wrote 1 year ago, which then contains an example of how you can solve the pairing model with neural network quantum states. So if you wish to expand your capability to solve the pairing problem, this is one possibility here. Now, in this specific code, which you see, we have done this in a very brute force way. So it's not very elegant, but it's set up mainly as a way to show you how you can encode it. You would actually have more efficient methods for solving these coupled nonlinear equations. So here we're just setting up the matrix elements, and you remember from the midterm that the matrix elements are just given by 0.5 times this constant G. And here we set up the matrix elements, making sure that they are properly anti-symmetrized. So you see now that we have the specific matrix element set up here, so that we can deal with anti-symmetrized matrix elements. And we need particle-particle, particle-particle hole-hole, and hole-hole matrix elements. And these are just set up here, as you can see. Not very elegant, but it works. And then we are setting up the Fock matrix for the pairing Hamiltonian. We don't need any particle hole term because we already are in a Hartree-Fock basis, as we discussed in the second midterm. So this is actually us now taking the second midterm and simply implementing the coupled cluster method. And here we set up the different matrix elements which are needed. And then we have the initializations of the amplitudes. And you see now that what we do here is that we're actually using these Fock matrix elements to set up the single particle energies. So you could actually set up the answer. So this is actually the first guess. These are the T2 amplitudes. Remember now that the T1 amplitudes are 0 because we are simply dealing with a CCD approximation, and we don't include the, due to the pairing problem, we don't need these terms here. So what you will find then, we do include it when we look at, sorry, I was not fully correct here. We do actually include this PP and HH terms in setting up some of the amplitudes, because some of the amplitudes actually require that. And you can see that from the, if you look at the amplitudes which we have, there will be amplitudes now which are of this type. So this is a 2-particle, 2-hole one. So this does not disappear because we have a 2-particle, 2-hole amplitude which contains the one-body term. So we need to include this term as well. I was wrong previously. I was a little bit too fast in my discussions because we have a 2-particle, 2-hole amplitude which needs to be included. So if we then go down here, I was too obsessed with the Hartree-Fock thinking. So what we have then is we have a guess here where we use the since we are on a Hartree-Fock basis, we have then the Hartree-Fock energies, which are then being set up here, as you did in the midterm. And then we simply now use the einsum, where we have the implicit summations, and we set up the different amplitudes, which you saw in that equation, which we have up here, in this equation here. So with that guess, when we plug in that one, we have then an expression for the new amplitudes, and we are setting them up here. We find the similarity transformed Hamiltonian. And with that one, when we then go down here, we set up the copper cluster energy, which then depends simply on these amplitudes, T, A, B, I, J. And then we multiply this with the matrix elements and then the amplitudes. And we have a factor of 0.25. And in this specific case, what we did was simply now to set up in a very brute force way. We just set up 6 iterations. There is no termination test, no nothing. And what we do then is that for every iteration, we find a new set of amplitudes solving these equations. And with that, we have now the new amplitudes, which are simply this T2 new plus T2. And then we keep iterating. And in this particular case, you see now that the energy with the copper cluster at the level of doubles only has roughly converged. And this is at the roughly the 10th or 11th digit. So we would say that this result has converged. And you will see now that we have a 36955.7. So there's a 36956. And if we go back to the original result we had from the diagonalization, you see now that at the level of the 2 leading digits after the decimal point, the copper cluster with doubles is roughly capturing the exact result. So the error is roughly at the order of 10 to the minus 3 to 10 to the minus 2. So which is pretty good. So copper cluster theory here does a better job than we saw with many-body perturbation theory for that specific case. So this is a summary of what we did last week. So we are now going to move into the new topic, which is the full derivation. After we reminded ourselves about the pairing model, we are now going to look at how we can derive the equations for singles and doubles excitations using first a diagrammatic expansion. And then we are going to accompany that one with a plain algebraic derivation. Okay, so let's now take a look at the derivation of the copper cluster equations for singles and doubles. And this is going to be a little bit more involved. So we're going to use the slides, which you see here. So let's just enter full screen modus here. So the derivations which we are going to look at now, they follow essentially what is given in chapter 10. Chapter 9 covers the derivation of the copper cluster at the doubles level, whereas chapter 10 is essentially what we are going to do in the slides now. So quick reminder, the equations which we want to encode are then given by this copper cluster approximation to the ground state, which is now given by the T1 and the T2 operator here. And the T1 operator is simply an operator with the unknown amplitudes, which creates a 1 particle, 1 whole state. And the T2 operator creates 2 particle, 2 whole states. And contrary to many-body perturbation theory, we now need to find these coefficients by solving a coupled set of nonlinear equations, whereas in many-body perturbation theory, every order perturbation theory gave us an improvement, hopefully, of these amplitudes. Now, just a quick reminder, we know that the Hamiltonian, which we have, is given in terms of these normal ordered parts with respect to the new vacuum, plus the vacuum reference energy. And the vacuum reference energy is defined here. Now, in the derivations below here, you will often see a notation which I have not been so how to say, fan of, but it's widely used in quantum chemistry. And if you go into the textbook by Shavit and Bartlett, they often shortened the integrals over the two-body interaction in terms of this term here. So you just skip the operator v. In the slides which follow, you will see that I've tried to adopt this notation as well. So what we are going to do now is first to look at the diagrammatic derivation. So this starts with us because we have a Hamiltonian which interacts with these operators t. And what we want to do then is to contract this Hamiltonian which acts on a specific state. So think of you making a one-particle, one-hole excitation, then we would definitely find out what is the contribution to the energy which comes from, let's say, Hn multiplied with t. So we want to find all possible unique combinations that satisfy given form. The diagram equation is then the sum of all these diagrams. So what we end up with then is to have to make contractions of these elements with 0, 1, or multiple t elements. And this follows from this expansion of the exponential ansatz for the wave function, where we have the similarity transformed Hamiltonian, which then comes as a, in terms of this Baker-Campbell-Hausdorff expansion. So let's just remind ourselves a little bit about that one. So let's now switch over to the whiteboard and quickly remind ourselves about some of these practicalities. So what we are doing is to look at the E minus t times this h of n of E. Just take away some of these things. Sorry. And what we have now is this E of t, which then can be written out as an h of n. And then we have this set of commutators where we have an hn of t, and then we have higher orders, sets of commutators, etc., etc. And then if we have a two-body interaction, then this set of nested commutators terminates at the order of 4 nested commutators. So what we are going to need now is a set of rules by which we can set up this type of contributions to the energy. We are going to plug this into the calculation of the correlation energy. So this correlation energy, delta E, is actually just the expectation value of phi 0 of E minus t of h of n E of t. And we went through the derivation last week. And then we have the other equations where we have a phi of IA multiplied with E of minus t of h of n E of t of phi 0. And if we stay at the level of just T1 and T2, singles and doubles, then these are the equations which we end up solving. So we have an h of n of v of t of phi 0, and this is also equal to 0. So that means that if we look at these nested commutators which we have, there will be several such contributions where we now have the Hamiltonian acting with t. So let's look at a specific contribution here. So let's take T1 and write this in a diagrammatic form. So T1, if we now think of many-body perturbation theory, so this T1 can be given by, so we have this TIA and AI. And if we use many-body perturbation theory, and in particular Rayleigh-Schrödinger perturbation theory, then this TIA is nothing but this integral with the operator f, and where we have an epsilon I minus epsilon A. So this was the contribution we would get to the approximation of first order for the wave operator, as we did in the second midterm. Now, if we then think of that, then this T1 here, diagrammatically, could then be represented in terms of a dot here, where this dot represents this specific integral. And then we have a one particle, one whole excitation, which is being created. So this is an A, and this is an I. And then if we look at a term like Hn times T1, that means that we are going to have an operator. So everything which you see here is going to be given in terms of a specific expectation value. So it's a vacuum to vacuum expectation value. And when we act with T1, what you actually have here is T1 acting on phi 0. And that creates, so we skip often this term phi 0, because what we have implicitly assumed here is that T1 has acted on vacuum state and it creates a one particle, one whole excitation, or it has acted on a given excited state and created a similar type of excitation. So what we would need then, when we are looking at this expectation value, would be to match the Hn. So if we think of Hn now as composed of a one-body operator, and we can write it like this, because the Fn, this is the Fn part, and then we have the two-body part. But we can have the more complicated types of diagrams. And we know now that if we look at this specific contribution here, this one represents a two-particle, two-hole de-excitation. This represents a one-particle, one-hole de-excitation. So that means that if I have a one-particle, one-hole state, then I need to de-excite it and match it with a one-particle, one-hole state to get back to the vacuum state. Now, this is normally given a number which is called de-excitation level. So we have a -1 here for a one-particle, one-hole pair, which gets de-excited. In this specific case, we have a -2 here. Now here we create a one-particle, one-hole state or pair. So we would then consider that one as a excitation level of +1. So the excitation levels here follow the number of particle-hole pairs which we create. So that means that in order to have a excitation level which is 0, so if we look at the ground state here, this is a 0 particle, 0 hole state. So this has excitation level equal to 0. So this is just a way to label the states here. So we call this excitation level. Let's call these levels. So we have 0, we have -1, -2, we have +1. And that means that if we take a two-particle, two-hole operator, then a two-particle, two-hole operator would typically be depicted like a thick line here, because this contains more than just the interaction. And we would write it like this. So I would have a state A, a state B, a state I, and a state J. And this operator here has an excitation level of +2. So when we now are calculating these type of expectation values, which follow from the application of the Baker-Campbell-Hausdorff expansion, we are ending up with terms which involve Hn times T, T times Hn, etc., etc. And every time they act on a specific ansatz for the ground state, and since we are only interested in expectation values for the correlation energy, that means that we have a vacuum to vacuum transition probability or expectation value. And then these are the type of excitation levels which we need to consider in the constructions here, because we are going to have at most a two-body operator. We can, however, have free particle, free hole excitations, four particle, four hole, etc., etc. So let's go back to the slides, because then this hopefully gives you a little bit of the nomenclature here. So let me just bring back the slides. This one. Just a moment. I just need to bring back the slides here. Okay, so screens. Yeah. So let's now take a full screen mode. So what we are going to do now is to contract these terms with multiple t elements. These t elements must at least have one contraction with hn, at least one, and that follows from the set of nested commutators. And remember now that if we look at the nested commutators, the t terms, they commute with each other. So that means that no contractions between t elements are allowed due to the fact that they commute. So a single t element can contract with a single element in many different ways. So let's now remind ourselves about some of the diagram elements. So we would then if we go back to what we have done, so these slides in a way serve also as a kind of reminder of what we did in the beginning of the semester. So we would have a particle line and a whole line, and external lines are connected to one operator vertex and infinity, and internal lines are connected to operator vertices in both ends. And these lines represent a contraction between second quantized operators. So when we now look at the one-body Hamiltonian, what we could say then, if we look at this type of excitation levels, so here we de-excite a one-particle, one-hole pair. Here we don't have a one-particle, one-hole pair. We have just a particle state in, a particle state out. So this is excitation level 0 because we stay in the same type of state. And the same with a whole state to another whole state. We call this level 0. And then here we create a one-particle, one-hole state. So this would be the one-body Hamiltonian when we look at the possible contributions. So the horizontal dashed lines, that represents a vertex, and the excitation level identify the number of particle-hole pairs created by the operator. So this is just what we put on the whiteboard here. Then, if we look at the two-body Hamiltonian, then we can rewrite that in terms of different particle-hole types of excitations. So the first one is a two-particle, two-hole de-excitation. In this case here, we de-excite a one-particle, one-hole pair. The same here. Here, we just have a two-particle state which propagates into a two-particle state. Here we have a one-particle, one-hole state which gets de-excited, and then we create one. So that's -1 + 1, 0. The same applies to a similar diagram. We can actually have the exchange of this diagram here, where you would have two whole lines, one whole line in, one out, and one particle whole line in and out. And that would be an example of an exchange diagram of this one, which also would have excitation level 0. So here we have two whole states in, two whole states out. Here we have a one particle, one state out, and two particle lines, one in and out. So this is level 1. Similarly, here we have another particle whole pair which is being created, and this is level 1. And here we have, finally, we have a two-particle, two-hole excitation. Now, we don't have a free-body Hamiltonian in the systems which we are going to consider in this course. So these are the type of excitation levels we have with the Hamiltonian. So when we then go back and we are linking h of n with t, what we need to do then is simply to match these different excitation levels. So if we look at the one-body operator, it looks like something like this. And this has excitation level 1. And similarly, the two-body operator has an excitation level of 2. So here we have created a two-particle, two-hole state multiplied with some coefficients. And now we are going to look at, after the break, we are going to look at the type of contributions which we get. So what we are doing now is to take the elements from T, the operator. So this comes from these commutators which we have with H and T. And then we take the elements of H here, and the final excitation level is 0. So we just mark that one with this empty box. And what we need now is simply to connect these diagrams for the Hamiltonian operator with the excitation levels which we have here. And we want to have excitation level 0, which means that if we look at these two guys here, the only possibilities which we have, which can match, is obviously this one and this part here. And this is what we will see after the break. Welcome back again. We are going to look now at the derivation of the equations for copper cluster theory based on a diagrammatic expansion. So we are going to bring back the slides again. And where we ended before the break was to look at these different excitation levels. And now, when we are going to calculate specific expectation values, we are going to need combinations of Hn with these different amplitudes. And we are going to limit ourselves to amplitudes which at most contain two particle two-hole excitations. So when we are going to link these together, we see now that we need to end at a final level excitation of 0. So if we have a +1, which you see here, then we need to link that with a -1, and we get a -1 from this one. We also get a -1 from this one, and from none of the other ones. The only problem then is that we actually left with a particle line coming in, a particle line going out in this case, and a whole line coming in and a whole line going out. We need to pay a little bit attention to these terms as well. But when we now look at the expressions for the energy, what we will have then is that since these nested commutators, they're going to contain a term with a T1 to the power of 2. They're going to contain a term with T2. So the T2 term gives rise to the one which you see here. The T1 will excitation level of -1 is this one. But then I will actually have a T1 times a T1, which is this one, and that is contracted with this final term. And that is the energy as we saw from the derivation, both from FCI theory, when we took the one particle, one hole excitations and linked that with the ground state energy. And we had then a contribution from the one particle, one hole excitations, where we got one from here, and we could get these two possibilities. And then we have the two particle, two hole excitation, which then gets de-excited. So these are the terms which contribute to the energy. And when we then want to label the diagrams and set up the final expression, these are just a reminder of the diagram rules. We label all lines, we sum over internal indices, we extract the matrix elements, F out, F in, left out, right out, left in, and right in. Then we extract the amplitudes with indices in the order left to right. So we would have, again, the same type of order, T out, T in, and then we have out for the left side and the right side, and the same with the in states. Then we collect the number of whole lines and number of loops. And then we have also the equivalent line factor, which is equal to 1/2 for every line or pair of lines which start at the same vertex and ends at the same vertex. So if we go back to the term which you see here, we have two lines which begin at the same vertex and end at the same vertex. So this carries a factor of 1/4. And then we have the summation of the internal state. So these diagrams here do not have such a factor. And then if we do that, we end up with the following expression where we now have used, and you saw an example of that in the program, this Einstein summation. So what you're having now is a summation over the repeated indices. So when you look at these expressions here, if you now rewrite these integrals as matrices, so this ij could be transformed into just one index, and ab could then be transformed to another index, then you see that these terms which you have here could actually be rewritten as matrices which are being multiplied. And in this case here, we could just have a multiplication of two vectors. And then here we have to be a little bit more careful, but we can still write this as a matrix, and then we can transform this quantity here as another matrix, and then perform the matrix, a matrix-matrix multiplication or a matrix vector multiplication. So if we do a matrix vector multiplication, then we multiply with a new vector. But these are technicalities which we will come back to. So just anticipate that a term like this one, for instance, is something which we can rewrite as a matrix-matrix multiplication. So in order to see that, I'm going now to anticipate something which comes later. Sorry. So if we look at this specific term here, the middle term, let's now just do that and then bring back the whiteboard. So if we have a term like this, so this is with repeated summations, but what we have is actually something which goes like this. So we have one divided, let's just use a blue color, 1 divided by 4 of a, b, I, j. And then we have the matrix element. We have an a, b, v of I, j. And this is multiplied with a t, I, j of a, b. Now the way we wrote that one in a more compact manner was in terms of this Einstein summation, where we have assumed that we sum over a and b and I and j. Now, if we look at these terms here, we know that we could now transform one of these states, two body states, a and b. We could transform that one into an index a. So a would then be the number of configurations which we could make, number of configurations when we now bring together particles A and B. If you think back to the pairing model, then this A and B would then represent one of the possible Slater determinants which we could make with two particles. So suppose now that we had this system here where we have only two particles, and we don't break a pair. So that means that this will be one possible configuration. And if we don't break a pair, this could be another one. And then we could have a new configuration, which is represented by this state. So if we don't break a pair, then we could make 4 different Slater determinants. So that would be the number of configurations A and B. In this specific case, A would then correspond to 4 configurations, and this A would then point to the different quantum numbers A and B. And then we could do the same with I and J. So we just replace that one with an index like that. So we would then say that this specific integral, this A and B, or ij, v, a, b, could then be replaced by a matrix with the subscripts I and A. And when we could do the same thing with Tij of AB. That could now be replaced with a matrix where we have the subscripts A and I. So that means that the summation which we have, this A, B, and if we leave out the factor of 1 over 4, this Vij, Tij, AB, that could be simply replaced by us setting up a matrix, IA, and multiply that with a matrix TAI. So in principle, actually what we're doing now is to sum over I and A, and we will simply write this as a matrix V times a matrix T. And that will be the compact notation which we will then use in this specific case. And this actually saves a lot of cycles if we then can set up a matrix with all the integrals instead of looping over a, b, and I, and j. Okay, so let's go back to the slides and stop sharing and then share the slides again. So the next thing which we need to look at is how we actually do the calculation of the T1 amplitudes. So when we look at the T1 amplitudes, what we want to end up with is now a final state which has a specific excitation level. So we start with a ground state, and in here we can have h times t and many other contributions. So this depends very much on the type of commutator which we are looking at. So we are going to end with a one particle, one hole state. So that means that we have this box here, and this is what we end up with. So in between here, we get something, and then we are going to end with a one particle, one hole state. So that means that the final excitation level has to be +1. So if we now look at all these diagrams for Hn and the T elements, we can then start looking at the possible contributions here. So some of these arise from different types of commutators. So obviously the first one is just this term here. Now we have a wave operator here, which then gets contracted with the Fn operator. Similarly, we have a term here, which also, this is with a two-body operator, which then produces a one particle, one hole excitation. So these are all parts of the equations for the amplitudes where we actually want to drive these to 0. And then you see here that we have a two particle, two hole state, which then interacts with the Fn operator, and that produces a one particle, one hole excitation. But we have an intermediate two particle, two hole excitation. So all these terms here are examples of diagrams which we can make with the T operators, the T1 operator, and also the T2 operator. So when we are looking at the possible commutator contributions, there will be T2 terms like this one here, and like this one, and similarly like this one, but this is a T2 times a T1, which comes in the commutators. This is a T1 squared. This is also T1 squared. This is a T1 cubed. And finally, this is a T2 times a T1. So all these are possible contributions which we can get to the amplitude equation for the one particle, one hole excitations. So the thing which we're doing now is simply to write down the possible terms which we have from the Baker-Campbell-Hausdorff expansion. And then we match together the different excitations levels, and we want a final excitation level of +1. And you see that in all the cases here, we have a final one particle, one hole pair. So all these intermediate states here, they lead to a one particle, one hole case. So this is the way we would set it up slowly, and we would again label our lines, sum of internal indices, extract cluster amplitudes with indices in the order left to right. We would calculate the phase factors and multiply by a factor 1/2 for each equivalent line and each equivalent vertex. And these are the equations which we will get then, where we now are summing over all the indices. So this is just the Fn term. And here we have an Fn times a T1, again an Fn times a T2, no T1, sorry. And the first ones there are actually this element, this one, and that one. And then the second one is us having a T1 term, which is being multiplied with a two-body interaction. So and if we then look at the term here, we have a T1 term, which is multiplied with a two-body interaction. Here we have a T2 term, which is multiplied with a one-body interaction, etc., etc. And here we are just setting up the signs, collecting the different factors, and these equations which we then can simply plug in a in a code in order to update the amplitudes. So it's doing this in a diagrammatic way is a very efficient way of setting up the equations. Now, when we now look at the equations for T2, then we are now going to end up with a two-particle, two-hole state, which is this state here. So we are taking the vacuum state, and then we are constructing the probability of making the transition to a two-particle, two-hole state. So the final excitation level has to be 2. And then we are going to match all these terms, which we get from the nested commutators, and we're going to match them with different final excitation levels. And again, oops, I wrote the figure wrongly. I didn't see this before. I have to update this one. But we will get a whole series of diagrams which where we now have just a two-particle, two-hole excitation. This is a one-particle, one-hole with a two-body operator for the interaction. There's a two-body part of the Hamiltonian with a one-body. There's a T1. Here we have a T2. And then in here we have a T2 with the Fn. Here we have Fn with T2. Here we have T2 with a two-body part, and this continues. Actually, many more diagrams. I didn't see this one before now, actually. And again, you will simply set up all the internal lines. Actually, in the textbook by Shavit and Bartlett, this figure is taken from chapter 10. You will see all the diagrams which contribute. Now, when we have this pair of lines, we have to anti-symmetrize the pair of lines. So we have to anti-symmetrize the two particle states and the two hole states. So that introduces this operator, which we discussed before the break. And the final expression is long and ugly. So we have many more diagrams. And when we start dissecting this now, you will see that when we look at the nested commutators, we will have the possibility of having T1 to the power of 4, because that connects with the final two-body interaction. So each leg here can connect with a leg in the two-body interaction. So I have a T1 to the power of 4. Here I have a T2 multiplied with T1 to the power of 2. Here I have a T2 operator with a T1 to the power of 2. Here I have again a T1 with T2, and they all lead to final excitation levels where we have a two-particle, two-hole state, as you can see indicated by the states which you see here. With M, this is a two-particle state, and this is a two-hole state, EF. And then we need to anti-symmetrize properly, and these are the equations we get. So as soon as we add singles and doubles, then the equations get more complicated, both for the singles and the doubles. If you think back to the copper cluster theory at the doubles level, the equations were much simpler. And also, we had for the pairing case, we had a much simpler interaction, which meant that some of the two-body matrix elements disappear. So you see clearly that if we now go to T3 and do copper cluster at the level of singles, doubles, and triples, the number of equations are going to be much, much longer. The number of terms is going to be much, much longer. Now, if you now look at what we have done, essentially these terms truncate a given order. So if you now look at the expansion we had to for the energy, these terms actually truncate in principle of this order. But for the energy, we actually only need to include double nested commutators. But for the two-particle, two-hole amplitudes, we need actually to include up to 4 nested commutators. So we had these terms with T1 to the power of 4, which comes from this nested commutator here, where T is actually the sum of T1 and T2. And if we look at the copper cluster energy, in principle, we can have plus here, but this actually terminates. And if we now look at the Hamiltonian here, we know that the Hn term, so what we are doing now is to go through this in an algebraic form, not diagrammatically. So the Hn term, since we are using a normal ordered Hamiltonian, This is obviously 0 because the expectation value with the ground state to the ground state, the vacuum ansatz, is only given by the reference energy. So what we need to look at then are the different commutators here. So if you look at the next commutator, this can actually be split into different pieces. So we would have this term here with T1 and with T2, and similarly with Vn of T1 and Vn of T2. So when we are going to do the calculations, we actually can, since we need the explicit expression for the commutators, both in the next term and in the amplitude equations, we would typically calculate them separately. So these terms which you see here, they will also pop up, some of them, in the calculation of the amplitudes. So it's actually convenient to look at these terms just by themselves. And when we do that, this is a simple exercise in just using Wick's theorem. And it's not the most exciting thing we're going to do, but I just wanted to show you how you can do this by hand. And that shows you quickly the strength of the diagrammatic approach. Because here we have to go through all these different relations. And we know that this is a term which we can actually rewrite like this. And then if we set up these terms here and we run through all the possible contractions which we can make, because now we are just using Wick's theorem. So we have the normal ordered piece we are setting up, and then we have the sum over 1 contractions and then 2 contractions. What we end up with is something which looks like this. And then if we use Wick's theorem, then what we have is this term here, and then we insert that into the original expression, and then we arrive at an explicit value of this commutator, which looks like this. So now we are just setting up the type of operators. So this product only includes terms where the operators are connected by at least one shared index. And you can see that quickly here because we have a shared index A here, and here we have a shared index I, and here we have again a shared index A. So these terms, I mean, this amplitude is connected with f of A here. And similarly, this amplitude here with I is then connected with f of I through I. So this is the terms which we end up with when we now have to calculate the given expectation values. So you see clearly, if this acts on the vacuum state, then we know that this one is a T1 type of excitation. So that's a 1 particle, 1 hole excitation. This one could be a 1 particle, 1 particle state. So you start with 1 particle and end with 1 particle. This is just a constant. So when we now let this commutator act on a given state, then we can quickly see what kind of contributions we are getting. And then we will do the same thing with this f of n with T2. So we can go through the same type of algebra and reorder these operators. This is again not the most exciting thing which we end up doing. So I'm just setting them up here for the sake of completeness. And if you feel tempted, you could try to repeat some of these exercises, or you could use symbolic Python to generate the what the nested operator actually gives us. So typically what you would do here, you would start with a rank-free operator, as you can see here, and you can reduce that one to a smaller rank for the operators. So with rank-free, I mean we have 3 particle hole pairs of operators. So when you then continue like this and bring everything together, this would then be the type of final operator you would need to plug in when you now act on this with a specific state, and then you have another state to the left here. So this is what it would look like when we collect everything. So we would have 3 terms, which then are all given by linked terms, as we can see here. So there's at least one common index in the operator for f, and in the amplitudes, either T1 or T2 here. So this is obviously a T2 term, so this gives us Fn with T2. And then we have to then compute the expectation value or the transition probability. And then we can continue this exercise because we would have Fn with T1 and T1. This is another set of commutators. And remember now that T1 commutates with T1. So this actually simplifies because we have this specific expansion already, which we can plug in. And when we do the algebra then, we get, after some tedious labor, we get that this can then be rewritten as an Fn, this operator, times a T1 squared. So if we go back to these specific analytical expressions which we had, so let's do that. So after we've gone through some of the analytical expressions, you will see now that there will be terms which could be of the T1 times Fn. But in order to get that one, we would have to go back to the T1 amplitudes. So you have an Fm here. This is a one-body operator. And then we have two T1 amplitudes, which are given by this term times this term. So these are examples of terms which you get when you now are looking at the T1 amplitude equations. So let's just continue a little bit and go quickly back again to where we were. So when we are setting up all these nested commutators, we end up with a series of final terms, which we then can bake in when we now are setting up the final expectation values or transition probabilities. So this one takes a simple form. So it has an Fn operator times a T1 squared. And then if we now look at the energy equation, one of the terms which we need to deal with is actually a term like that one. And we know then that since we have a normal ordered operators acting on the vacuum state, then this commutator here has simply to give us 0. So that term is actually 0. If I then continue, what I will get then when I do all the algebra here, I'm getting this specific term here, which is the one we have seen before. So we get this VNT2 here. We are plugging in the Hamiltonian operator. We plug in the two-particle, two-hole operator, and then simply perform all the possible contractions using Wick's theorem. And when we do that, we end up with an equation which we have seen before. So that's where this arises from this set of nested commutators. So that means that the energy, the CCSD energy, gets two contributions from this H of n with T, and one contribution is this one, and the other contribution is that one. And these are the only two contributions which you get. So if we go back then and look at the equation we had for the Baker-Campbell-Hausdorff expansion, so let's just quickly do that. And if we look at the energy here, actually this terminates at this order here. So this Hn, as we said, is by construction equal to 0 because we're using a normal ordered Hamiltonian. And then the only term which then contributes is actually this one. And that's the one which we put up after all these lengthy and exciting calculations. We ended up with the term which we see here. So that was for the energy. And then we can actually use these nested commutators to find the same expressions which we did before. And so the energy equations, if we now labor through it, we will also have to be a little bit careful here because we have an additional term which comes from this one, which we left out, which gives us this term here. So when I add everything in terms of these amplitudes, I have this term here, which then has to be included together with these terms which we saw here. So we get a specific term from T1 squared multiplied with the Hamiltonian. And for the T1 squared term, we know that in that case we need a two-particle, two-hole de-excitation. Okay, so when we look at the Energy equations, we see that there are no contractions which are possible between cluster operators. They need to contract with three indices to the left. Disconnected parts automatically cancel in the commutator. One-body operators can connect to maximum two cluster operators, and two-body operators can connect to maximum four cluster operators. And these are four T1 operators. So the one-body operators can have at most two cluster operators. And different terms in the expansion contribute actually to different types of the equations. So one of the things which we can discuss now is this factoring. So if you look at a term like this one here, this is a typical diagram which you would get. So you have now an Einstein summation. So we are summing over M and N. We are summing over E and F. We are summing over I and J. And we are then also having the final A and B. So we want a final product which has states I and J and A and B. So this is actually what we want here. So we have also other terms. There's another diagram or full list. These are diagrams which are taken by the textbook of Shavit and Bartlett. So if you now look at this specific diagram, if we now go back to that, we see that this one can be rewritten in terms of an intermediate calculation. So what I could do now, if you look at the final indices are I and J and A and B. So we have a final state I and J coming in. We have an outgoing particle state A and an outgoing particle state B. And we have intermediate states here which we are summing over. So we are summing over M and N and E and F. And then we end up with a final term which depends on I and J and A and B. So what we could do now, if you now look at this intermediate state here, we could perform the matrix multiplication. So if you think back to what we discussed before the break, we can think of this as a matrix and this as a matrix. And we simply call that matrix for a matrix X with where we now have performed the summation over E and F. So that leaves us with coefficients with the particle states M and N, as you can see here, and the indices I and J. So we simply perform this calculation by summing over E and F. By doing that, we get a new matrix, and this new matrix has the subscripts M and N and I and J. So these are terms which can be calculated before we actually perform the final calculations here. So these are so-called intermediates. And many of the diagrams will actually contain similar terms. So that means that we can pre-calculate, and that saves CPU cycles. So if we pre-calculate, then we can then just perform a matrix multiplication at the end. Because here we are summing over M and N. And at the end, what we want to have is a matrix which contains I and J and A and B as possible states. And if I look at this other diagram, this diagram which you see here, where I have a T1 times a T1, and I have a T2 here, then I recognize this as a TABMN and MNEF. So if I now isolate this part which has A and B here, and recalculate, if I take X, this same matrix which I had before, and I collect this I and E here, I can actually set this up in terms of this same contribution, XMN, which has a shape like this one. So I pre-calculate it, then I can multiply that one with this TIE, and I can define a new matrix. And this will also be an intermediate set of matrices. So it's a matter of you finding out some specific contributions, which you then can reuse in the calculations of other diagrams. So this is one possible way by which we can factor many of these diagrams here. The same thing is something which I can do with this diagram, which has a T1 to the power of 4 and multiply with a two-body matrix elements. So what I could do now is simply to start collecting terms and produce something like this X of EJMN. So I'm collecting this term MNEF with the matrix elements of the T operators, which contain subscripts J. And if I do that one, I can then set up this as an intermediate. And then I take the next term here and I have a new intermediate which I can calculate. And since I'm going to have another case where I have a T1 cubed, I can actually define a matrix so that I have a T1 cubed times a two-body matrix element. I can then identify a new final intermediate here in terms of this new matrix Z. And then I can perform the multiplication here and run over m's. And then I will end up with a final term where I have A and B as outgoing particle lines and I and J as incoming whole lines. And you see now the diagram here, you have two incoming whole lines, I here and J here, and two outgoing particle lines, A and B here. So this is a very compact way by which we can actually rewrite the diagrams and where we have pre-calculated terms like these. So you can then, when you run the calculations, instead of us performing, if we now go back to the equation which we had, so let's just go through that equation. If we look at the equation for the T2 amplitudes, here, so what we have here is actually a summation of all the indices. If we do that, then clearly, in order to end up with a state AB and IJ, which is where we are ending, because these are the equations for TIJ, then what we can do is to calculate many of these intermediate terms and then perform efficiently matrix-matrix or matrix vector multiplications. So this is a trick which is called the factorization trick and is widely used in couple cluster calculations, but also in many-body perturbation theory, because there's nothing which hinders you when you look at terms to third order and fourth order to identify terms which can be factored and then pre-calculated and reused in high order terms. And that saves a lot of CPU cycles. So you can actually say that a diagram can be classified by how many whole and particle lines between a T1 operator and the interactions. So you could then have a given number of particle hole diagrams. So if you look at in this specific case here, you have this diagram has two T2 amplitudes multiplied with an interaction. And in that case, we have two particle states and two whole states, which we need to deal with. And this is a way to classify the diagrams in order to figure out which one can be factored. So in this specific case, we would have a diagram here where we have two whole states, which we are summing over. And we will have a particle state and T1 and T1 here. Finally, if you look at this diagram here, we will then have four diagrams which now contain either a particle state which is summed over or whole state which is summed over. So you can see that because this one has a whole state which is summed over. This term here has a particle state which is summed over. So we have a whole state coming in. We have a particle state leaving. But then the intermediate guys are summed over. And that gives you the kind of, how to say, estimate of the numerical expenses which you will have. Here you're summing over another particle line, whole line, and here sum over another particle line. So you have two summations over particle lines for T1 and two summations over whole lines for T1. And if you go back to the previous diagram, you see now quickly here that you have two whole lines here you also have two parts. So you have two whole lines which enter the T2 amplitude, and then you have two particle lines which are summed over in the T1 amplitudes. Okay, so if you now look at the copper cluster algorithm, so you would typically set up a model space. So this model space contains actually all the single particle states you want to deal with. So that is your effective Hilbert space. And then you set up the V and F amplitudes. So these are the integrals which we need to set up. And then we have an algorithm for finding the energies. So we calculate the reference energy that has to be calculated. And while not converged, we take the new energy minus the old energy, being larger than the number we want to estimate. We calculate the intermediates. So we have the new values. And then with these, we calculate the energy. And this continues till the energy minus the new energy minus the old one doesn't differ by a final value epsilon. And this concludes the algorithm. And that was a case which was included in this pairing model algorithm. Essentially what we did was to perform this set of iterations, except that what we did then was not to have an if test, if converged or not. Okay, so this in a sense wraps up the description of the copper cluster equations at the level of the T1 and T2. If you go to the textbook of Shavit and Bartlett, you will find examples in chapter 11 and so on how you can include the T3 amplitudes. But the basic thing here is that you have a certain feeling of what goes on and what are the basic calculational elements which you need to set up. So when you have these amplitude equations, there are ways by which you can simplify the calculations by factorization, and you will do that with all the equations you have. And when you've done this factorization, then you can set up the iterative solution for the amplitudes.